Let's look at Chapter 1, Limits Review Worksheet. So number 1, we're given piecewise functions. This g of x is a combination of line segments, points on the graph, segments, rays. So all these separate parts make up g of x. So we're going to be answering these parts using this piecewise function. So part A says find the limit as x approaches negative infinity for this g of x. So as we approach negative infinity, we want to find the appropriate definition for that. So as x approaches negative infinity, that is going to fulfill this condition where x is less than 2. And if we're dealing with infinity, then we can plug in a large negative value to express that that direction. So if we plug in a large negative value into this expression will continue to approach negative infinity. We'll get the value will get larger and larger in the negative direction, so negative infinity. Okay, part B, limit as x approaches 2. As a one-side limit, x approaches 2 from the left side of 2. So as we approach 2 from the left side of 2, sometimes the tendency is to just look at directly at where the ordered pair is and provide the answer. But here we're only looking at the limit from the left side of 2. So we have to look at the behavior of the y value as the graph approaches the x value of 2 from the left side of 2. So from the left side of 2, the condition that will match is going to be x is less than 2. So when x is less than 2, we're using this expression. So if we plug in 2 into this expression, we get 2 plus 5, which is 7. Okay? And if we're evaluating one-sided limit algebraically, the first thing we do is we just plug in that value, ignoring the one-sided limit. The one-sided limit in this case is just going to help us identify which piecewise function to use. We're approaching 2 from the left side of 2 and not from the right side of 2. From the right side of 2, if it's 2 plus, then we'll use this expression. 2 minus, we're going to use the first expression, x plus 5. Okay, part C, limit as x approaches 2 from the right side of 2. Now this, we're going to be using the expression, this condition here. This fulfills the condition 2 from the right side of 2. So if we're approaching 2 from the right side of 2, we're talking about 2.1, 2.001, 2.0001. So all that is going to fall under this category where x is between 2 and 5. And so we'll be evaluating the limit as x approaches 2 from the right side of 2 for 2x minus 1. So 2x minus 1, we just replace x with 2. So 2 times 2 is 4. 4 minus 1 is 3. Part D, limit as x approaches 2. So again, the tendency is students may want to directly use the order pair that's provided. The order pair is 2, 11. So but we have to be careful because it could be the case. This will definitely be the case if it's asking for f of 2. If it's only asking for the order pair at 2, then 11 will be the right answer. But if we're approaching 2, that means we want to see does the graph approach the same y value from either side of 2. So in other words, if we evaluate the limit as x approaches 2 from the left side of 2, is that going to agree from evaluating the limit from the right side of 2? So we actually found the one-side limits for part B and C. So for part B and C, approaching 2 from the left side of 2, it'll give us 7. From the right side of 2, it's going to be equal to 3. Now, in order for a limit to exist, the graph has to approach the same y value from both sides of that x value. So from the left side, it's approaching 7. From the right side, it's approaching 3. There's going to be a disconnect. The graph does not approach the same y value, so therefore a limit does not exist. Okay, next part, limit as x approaches 5 from the left side of 5. So from the left side of 5, we want to choose the appropriate piecewise. So from the left side of 5, we're talking about from 4 to 4.9, 4.999. So that's going to fulfill this condition. So we'll be using the 2x minus 1. So limit as x approaches 5 from the left side of 5 for 2x minus 1 will simply be equal to 9. If I plug 5 in for x, I get 10 minus 1, which is 9. Approaching 5 from the right side of 5. So again, we go back to our piecewise. From the right side of 5, it'll fulfill this condition here. So 5.1, 5.001. If I plug in, so we're going to use this last piecewise function. So plug in 5 in for x. 5 plus 4 is 9. Okay, for g, limit as x approaches 5. In order for a limit to exist, again, the tendency is we want to just look at the order pair, but the order pair may not give us the correct behavior from either side of 5. So for g, we can actually refer back to what we found from E and F. We found the limit from the left side of 5. We found the limit as x approaches 5 from the right side. We see that they agree. So therefore, in order for a limit to exist, the one side limits must agree, and they do. So the limit is equal to 9. Okay, next part, approaching 6 from the right side of 6. Now we don't see 6 as a parameter here, but anything to the right of 5, we're going to be using this expression. So it could be approaching 7 from the right side of 7, approaching 9 from the left side of 9. These all fall under this category. So we can simply use this piecewise function and then evaluate algebraically, plug 6 in for x. 6 plus 4 is 10. Right, approaching infinity. So approaching infinity, we see that it'll have to be greater than 5. So greater than 5, if it's approaching infinity, we just plug in a large representative value, like 100 or 1,000, and we see that this expression, this will keep increasing, and it will go to positive infinity. Okay, number 2, use continuity conditions to justify whether f of x is continuous or discontinuous. If discontinuous, identify each type of discontinuity. Okay, just to review, continuity condition. First is, does the point exist? Second, does the limit exist? And a lot of times we may have to go a little bit further and test the one-side limits from the left side and from the right side of C to see if they agree. Okay. And then the third condition is, does the order pair exist at the same point where the limit exists? Okay, so we compare the results from the first and second condition, and if they agree, we know the function is continuous. There's no breaks in the graph through that point. The graph will be continuous through that point. All right, so determine the function is continuous or discontinuous. We're always paying attention to where the potential break could be in our graph. We know that x squared plus 5 is a polynomial. X squared minus 2 is a polynomial. Normally, we don't have to worry about any breaks in the graph. However, this is a piecewise function, so we have one segment that's only existing to the right side of 3, another segment to the left side of 3. So there is a potential for the graph to be disconnected at this point 3. So, so even though the problem doesn't specify where the point of discontinuity is, we can look at the piecewise function and be able to make that conclusion that the point that the point of interest here is at x equals 3. So first thing we do is decide, does the point exist at 3? So does the point exist at 3? We look at the condition that will match where x equals 3. So x equals 3 for the first piecewise, greater than or equal to 3. So if I plug 3 into the first piecewise function, I want to find where the order pair exists. So plug 3 in for x, 3 squared plus 5, 9 plus 5 is 14. So the order pair on this graph exists at 3, 14, at the y value of 14. Okay, so because there's a piecewise function, one that's existing to the right of 3, the other to the left of 3, we can test the one-side limits on either side of 3 to see if the y values will agree. So from the left side of 3, that will be the second piecewise, x squared minus 2. For the second, on the right side of 3, it's going to be x squared plus 5. Okay, and then both limit expressions we can evaluate by plugging 3 into x. The one-side limits, a lot of times we're going to be able to ignore that unless we try to plug in and if we get undefined. If we get undefined, then we have to go do a little bit more work in terms of determining whether there's a vertical asymptote and whether the graph is approaching positive or negative infinity. So if we plug in 3 in for x, we get 9 minus 2, which is 7. If I plug 3 in for x here, I get 9 plus 5 is 14. We see that these values do not agree. So from the left side of 3, the y value is approaching 7. From the right side of 3 is approaching 14. So the graph is disconnected. If it's disconnected, we know the limit doesn't exist. If the limit doesn't exist, the second piecewise function fails, and therefore we know there's a discontinuity. It doesn't pass all 3 tests. If the second condition fails, we call that a non-removable discontinuity. There's a break in the graph when the second condition fails. All right, part 3. Find the value of k that will make the function f of x continuous. Now this is different. This piecewise function is different from number 2. Here we have 2 separate branches. One branch to the right of 3, the other branch to the left of 3. Here, there's the 2 branches are actually connected, are contained within this first piecewise function. The only place where the graph could be disconnected is at negative 3. So there could be a hole in the graph at negative 3. However, the way that this expression is set up, this piecewise function is set up, we don't have to do one-side limit as we did for number 2. The 2 separate branches are actually contained within this piecewise. So, but we can still go through our conditions here. Right, find the value of k that will make the function continuous. We don't know where f of negative 3 is, so we're going to skip that. We'll come back to it later. The second condition is seeing does the limit exist. The limit does. We're going to evaluate the limit as x approaches negative 3. So on either side of negative 3, we're looking at the first piecewise, so we can just evaluate this directly. So if I plug in negative 3 into the expression, I'll get 0 over 0. So if I get 0 over 0, that indicates that there's a this function is that's indeterminate. So that tells us if we get 0 over 0, we have to continue evaluating the expression. So what we can do is we can factor the numerator into x plus 3 and x minus 2. That will match the denominator of x plus 3. If we cancel out the hole in the graph, we can reevaluate the expression. So negative 3 minus 2 is negative 5. So we know the limit exists at negative 5. So in order for the function to be continuous, the k value would have to be negative 5 in order to cover up that hole in the graph. So this is what the graph looks like. X squared plus x minus 6 over x plus 3 looks like it's basically just a straight line with a hole at x at negative 3. And then that negative 3, which is undefined for the first piecewise, can be covered up by the second piecewise function if we just replace k with negative 5. If we replace k with negative 5, then we can fill in that hole nicely. If that hole fills in nicely, then our function is continuous through x equals negative 3.